Our presenter tonight is Dr. Jasna Martinovic from the School of Psychology at the University of Aberdeen. Jasna is going to be talking about her research in vision science and how knowledge about human perception can feed into the development of cutting-edge display technologies. So I'm going to hand over to Jasna. Thanks.
Thank you, Jen, for that lovely introduction, and thanks everyone for coming. I hope I won't disappoint you. So I guess you came because you're interested in technology, display technologies. I guess cinema is also a really lovely venue for an event like this. You might be wondering how exactly do different disciplines communicate, because it's actually quite different when you're an engineer and when you have to find solutions to design hardware that's efficient, that works very optimally, that works to a certain specification, and a sort of maybe a little bit we are often perceived as boffins who sit in labs, who conduct experiments and produce data, and where do these two things meet? So in order to sort of give you a little bit of perspective, I think first I'll give you a little bit of a background as to what I do and how I collaborate with computer science in the display of technologies, and then just take a little bit of a detour and discuss actually why can't we just design equipment without consideration of these factors, what sort of errors might ensue, and looking a little bit at the history of development of technology, because that can actually inform us how things got to where they are. And I actually, in order to give you a few examples, I also brought some glasses that simulate color vision deficiency as the most frequent one that exists in the human population. So I will, once I introduce that concept, I'll also pass them around, and you can all kind of get to experience that. So yeah, to begin with, as Jen said, I'm from the School of Psychology, but normally when I go into a taxi, I say I'm a scientist, because I don't want people to say, oh, I know, so now you're a psychologist, you must know what I think. So I say, well, I'm a color vision scientist, and that's actually quite a good conversation starter, I discovered, because people go, well, so some people actually react, well, what is there to study? Don't we know everything about how this works? And that kind of mimics how, I remember when I was a kid, and there was a psychology book in my house from my older cousin, and I actually remember just opening the middle pages with the visual illusions and just looking at them and looking at color after images on the wall and just being fascinated by that. But actually now when I work at the psychology department, a lot of my students actually think that perception is very difficult, very boring, so I sort of believe that what I do is really boring. But then when I actually meet members of the public, then I start getting more excited that it's not the same. So in a sense where everyone thinks that the psychologist can tell you what you think, or somehow can read in people's minds, I actually can tell you how you see color, and I'll be correct 90% of the time. So, because 90% of humans, as long as the visual apparatus and the brain are undisrupted, will perceive colors in a very, very, very similar way. So the big question is, how did we evolve to be this way, and what mechanisms control all these multiple aspects that control appearance of color? So you've all experienced various phenomena, such as when you see a color surrounded by other colors, its appearance changes slightly. Appearance of colors depends on the overall level of illumination. So we've all experienced that actually it's not kind of, our eyes don't work as a sort of a measuring device. So our eyes don't work as a photometer. And that is the reason why we need to know how humans perceive color in different contexts, so depending on the size of the stimulus, or the pattern of the stimulus, or on the adaptation level of so how much illumination is around you, or the differences in light levels in the image, the appearance of things will actually change depending on that. And that is why actually the engineers who design display technologies are very much interested in knowing these things, because if our eye worked as a simple physical device that measures the quantity of light at a certain set of pixels, you wouldn't need to know anything else. You would just need to design something that reproduces that accurately. But that's not how it works, and the reason for that is that actually color is in the mind of the observer more than in just the eye of the observer. So it's not like we have some instruments that are wired into our brain and feed it correct information like some sort of absolute truth. There is no absolute truth, there's just the relative truth. And this is what's interesting about color. And I would now like to take a little detour into color vision, just to get us all on the same ground level before I can then talk about how these things lead to applications and what sort of things we do. So to think about color vision, we should think about how color vision evolved. So if we think about mammals, mammals normally have two receptors in the eye. So they have a short wavelength receptor, which is tuned to maximum sensitivity in the short wavelength part of the spectrum. And they have a long wavelength receptor, which is tuned towards the long wave. So when I talk short and long, it's actually a very, very tiny part of the actual physical spectrum that is the visible part of the spectrum. So these are somewhere around 440 nanometers would be the short wavelengths, and around 680, 700 would be relatively longer wavelengths. So this is a very narrow part that we actually perceive. And the mammals used to be mainly nocturnal. Because when the mammals evolved, they were very small animals, and to avoid large predators, they were normally they would be active in the dusk, and they would hide during the night. And therefore, if you actually think about what you can see in the dark, you wouldn't be able to see lots of color. And actually, we were just turning up the lights earlier in the room because I wanted people to be able to try the glasses and see differences in color. And when it's dark, it just doesn't work that way. So it's kind of pointless to have lots of color vision receptors if you are a being that functions during the night. Unlike mammals, birds have 4 receptors, and there are some creatures in the sea to whom color is incredibly important, and they have 9. So there are some crabs that actually have 9 color vision receptors. And obviously you can study what things they can tell apart, but you can never actually know how these things appear to them. You can try and run some simulations based on how things appear to humans, but you will never know. We know how things appear to us, and we know how things appear to other mammals by proxy of humans who miss one receptor. So humans evolved an additional, our primate ancestors actually, which needed to discriminate more colors, they evolved another receptor, a middle wavelength tuned receptor. So now they were tuned to one part of the short wavelength spectrum, and now they actually could discern more differences in the middle and long wavelengths of the spectrum. And this, instead of just being able to tell between bluish and yellowish, also allows you to tell between reddish and greenish colors. And actually, the glasses I brought, I'm going to pass around now, and you can just put them on and have a look. What they simulate is having only 2 receptors. And what you will experience, if you look around, you will see that there are some brown seeds over here and some red seeds. They are going to look exactly the same when you try on the glasses. And the only colors that will maintain the same appearance will be blue and yellow. So I'll just pass around the second pair. You can just pass them around, try them on. So why do we need to see more colors, and how did our brain actually, if you think about, this is the most recent evolutionary, major really evolutionary change, an evolution of a new receptor cone to gain the ability to actually tell red from green. Without this additional receptor, you cannot tell red from green, and you will experience this when you try on the glasses. Now, with an addition of a new receptor, our brain actually has to rewire itself and somehow adjust the output of all of these receptor systems so that they all can appear equally saturated, equally salient when they are of relatively comparable intensities in the environments, and all of that so that we can tell properties of objects. Because actually, properties of objects, such as ripeness of fruit, for example, or freshness of green leaves, are incredibly important for survival of the species. So if you think about the species that evolved this system, the primate species, and then you can see how actually, even today when people talk about things, think about when you teach children how to speak, very often it is actually the color words that are among the first that we teach children. So I often say to my students, if we think about the visible spectrum as a range of frequencies of light, and then if we think about musical pitches as a range of auditory frequencies, I often tell my students, if we talk to our children as much about what sound is which pitch, so if you play a pitch and then you say A sharp, B flat, you know, D or C or whatever, everyone would have perfect pitch, you know. So actually our society is very interested in color. And now, I'm happy to talk later. I don't want to just bore you with color vision because I know you're all interested in technology, so I would like to switch gear again. But if anyone has any more questions about color vision in nature, evolution, I'm happy to answer those questions later on. But now that we thought about this, so color is really important to us, and we like to see the world of color. And when you try on the glasses, you probably have an experience of a very impoverished world, of a very impoverished image once lots of colors drop out. So how did we develop technologies that display images? So if we actually think about the development of photography or television or cinema, first it was black and white. And because the challenge of just capturing differences in the intensity of light was much easier to solve than the challenge of getting some sort of realistic colors to appear in those images. And actually, even today, the way we get color into images is still a little bit of a fudge, but it's a fudge that works really well, and that's what engineers like. It's kind of, I work with so the engineers I work with, they're computer scientists from the University of Cambridge, and they just always say to me, what you see is what you get, Jasna. It just has to be that it looks right. As long as it looks right and then it works, it doesn't matter how. So this is the engineering approach. But actually the scientific approach can benefit a lot from that, in my experience, because often scientists become obsessed with relatively tiny effects that don't really have real-world relevance. So I think actually engineers and scientists talking to each other is very fruitful for both perspectives to develop. So we started adding color to photography. Initially, people would just paint the colors in. And also in terms of color films and color television, there was initially that stage where you already had films that were recorded, and then there was a process of let's try and edit with pigment and let's see how that looks. But ultimately, the big challenge is how do you record light so that you already record light in a way that can separate different components of color. And that's where the whole RGB comes in. So engineers early on figured out that actually you can, if you capture a sort of a record of the bluish, so very short wavelength part of the spectrum, and then greenish, and then the reddish, so you sort of capture these three parts of the spectrum, and then you overlay them, you can actually recreate color in a very, very good way. And this is basically in different ways. I've read a book about history of development of display technologies. I'm not an engineer, but I know some of these things. So again, if any of you are very interested how some of this works, I can attempt an answer or direct you in the right direction. But actually what is interesting here and why engineers need me is because the appearance of color cannot be predicted simply by measuring the intensity of light at certain wavelengths. It depends, as I said before, it will depend on the size of the patch. So once patches become very, very small, and especially now that you have very high resolution of screens and display devices, once the patches become very, very small, images, that part of the image will lose saturation. So it will actually start to look less saturated than it should if it was a larger patch. It depends on the spatial pattern. So if you have large patches of light, then those are perceived in a much more stable fashion and more independent of the surround. But actually, if you have a dense, spatially dense image with different patterns, so like let's say small elements of different colors, different brightnesses mixed together in a narrow area, the appearance of each of these individually will not be independent from each other. So I can tell you a little bit about the types of experiments we do, which is then used for these implementations, which actually adjust what's recorded based on the spatial distribution of these colors. So kind of you can think of it as boosting certain channels as opposed to other at certain locations of the image, or depending on certain attributes of the image so that it looks good. So these experiments are probably why everyone in my department thinks that what I do is incredibly boring, by proxy of the fact that my experiments, I'm not advertising them too well here, I guess, but mainly people sit in the lab for hours and hours and hours. I can see my PhD student laughing there. You sit basically and all you do is you adjust. I give you a patch of a color or a pattern, and I give you another patch that varies along the particular dimension that I'm interested in or that Anna is interested in. And then the participants, they adjust a property, such as, for example, they adjust the saturation, or they would adjust the hue of the stimulus until we get a match. And this appearance match is something that is very typically human, because, for example, you can do a lot of experiments in non-human mammals, but you can see what they can tell apart by seeing if they can learn to press a button when one thing appears and not the other. But you cannot do experiments based on appearance, because you can't really explain to them concepts such as saturation or hue or things like that. So it's something that actually is very much studied on the human model, because the concept of redness or blueness or greenness is a very human concept. As I said, it's in the mind, it is not anywhere else. So once we have data from these experiments, and also we also look at visibility. So we don't look just at appearance matches, we also look at visibility. So depending on the spatial pattern or the size, can you actually, how little contrast, so how little light energy do you need to be able to tell that something was there as opposed to not there? So for example, I could have 4 locations on the screen, so like a 4-quadrant type of display, and participants know that in one of the 4 quadrants there will appear a stimulus, and they have to say in which quadrant the stimulus appeared. They have 4 buttons that correspond to these locations, and I measure just how little energy of light they need in order to be able to do that task. And then we can define the contrast sensitivity function depending on the color energy or the brightness energy. And once you have all these are actually fed into the software that adjusts the appearance of images so that it maximally benefits from the potential resolution of the screen. So for example, imagine if you have a really high resolution screen, like iPads actually have pretty good spatial grid on their devices, but the software actually just shows an image as it was recorded without any adjustment. So let's say if you have a film from the let's say The Wizard of Oz, one of the first beautiful color films, but without any adjustment, you wouldn't actually be able to benefit from this, and it would start to look awful. So there's a lot of need for actually back compatibility. This is something that in industrial development, so for example, when color television was being developed, one of the major challenges in the development of color television was to ensure that the new display devices could show what already existed and show it as a good black and white image, but also that when you broadcast the color signal, that it could be received by all the people who have black and white television, because otherwise there'd be a revolution on the streets of America with all the people who already owned black and white televisions and who wouldn't be able to use them anymore. So being able to retarget, so in engineering this is called retargeting or tone mapping. So being able to remap appearance between different devices is very important. So one thing that this also enables, and this is something I work with my colleagues, so this is a collaboration actually between psychology in Aberdeen and psychology at the University of Liverpool and computer science at East Anglia and at Cambridge. And one thing actually that we want to do is we want to have screens that actually are adjustable. So for example, as visual systems age, so as people get older, there is a different sensitivity to sharpness of the image. So people actually prefer sharper images, or say if people develop a cataract in the early stage and it's not yet at the level where it would be operable or that it's worth operating on, color appearance can change a little bit. So the furniture can, I had one participant in some focus groups that I run, and the participant said, oh, actually I made such a big mistake, I bought new furniture before my cataract surgery and now it looks so brown and so awful. So one thing that's very important to develop is actually to make these devices look good for the individual user. So if you imagine now that we can all log on to our computer and we think that's normal and people share the same computer, well, why not when you log on, it loads a certain set of parameters that you adjusted yourself and now the image looks really good to you. Or, for example, tablets or phones that you use outside, they could detect themselves the level of illumination that they're exposed to and then adjust the display of the image to this new amount of light. So this is something that once you have all these measurements and you know how people see things in certain environments, you can actually introduce this tone mapping and retargeting. And as I before passed the glasses for simulating color vision deficiencies, I'd also like to end on a note of some developments by our partners from East Anglia, and they are actually developing adjustment of appearance so that people who have a color vision deficiency and people who don't have a color vision deficiency can watch television together and it looks good to both of them. So this is, I don't know if any of you have themselves or have family members with color vision deficiencies, but this can pose certain challenges because, especially if you, for example, watch sports. Now imagine you've all tried the glasses now. Green will look yellow and red will look yellow. Most football teams have red shirts and they run on green grass. So that poses certain problems. The ball isn't like it used to be black and white, but now actually designers start to use color in more inventive fashion. They actually forget that 10% of the population cannot see it in this way. And actually, these glasses that I passed around, they're called universal design glasses. And actually, the biggest customers are designers who buy them in order to make sure that they don't make maps or they don't make applications where information is encoded in color so that people can't see it. So actually, I've seen what Spectral Edge do, and they sort of generate a system where the image is encoded in a way in which a person with a color vision deficiency can see everything very, very nicely, and then they produce multiple versions of this, and they get observers with normal color vision to rate how much they like them and how more realistic, obviously it's not going to be completely realistic, but how it looks to them, and coming to a solution where now a family can sit and watch sports events or whatever programs together and share these experiences, which I think that's fantastic. So just to wrap up, since my time is nearly up, I have found working with designers of display technologies really fascinating, and I've only worked on this project for the last 2 years, but I envision that now that I got a taste of it, I will continue in that direction. It does take some time for, I'm relatively early career, I only got my permanent position in 2009, so 10 years ago. I think it takes some time for a scientist to want to see the bigger picture and to lift the head up from, let's say, well, for some people it's the microscope, for me it's just my colors on my monitor, and to see, I want to make things that can be applied, I want to make things that are useful to people, rather than just studying some very, very small phenomena that are of narrow scientific interest. Contributing that way to not just technology goes somewhere, but technology goes somewhere for the benefit of all of us. So thank you very much. I hope that you enjoyed this presentation. I look forward to receiving your questions after the break.
So this is a question about color balance.
Yes.
So digital cameras, video cameras have some sort of automatic color balance control, but sometimes it gets it wrong. So like if you took a photograph inside in an artificially lit room, it might look yellow, for example. But the human eye seems to do this automatically. How does that work?
So the human eye actually adapts to the level of illumination very, very quickly. And the achromatic setting of the human eye, at our current level of knowledge, we believe that actually it's recalibrated continuously. So constantly we sort of use the appearance of the colors themselves to recalibrate where the neutral setting is relative to what the assumed illumination is, as well as what colors are present in the image. So depending on that, we can sometimes get deceived, and that's where you sort of have visual illusions, which are actually extremely rare scenes that you don't really normally encounter in everyday life, so we haven't evolved the capability to deal with them. Now, why the cameras sometimes get it wrong is because there are different models for human adaptation, and different color systems use different systems. So for example, color appearance model such as CIE-LAB uses the von Kries adaptation, but that actually only functions under a certain level of overall illumination or whatever, so there is no absolute formula that accounts for everything. And then if you actually, in an image, if you don't have enough different colors so that the system can use that to sort of use a shortcut, you actually end up with, so that's why it often happens with indoor illumination, because of this general iridescent lighting shifting the balance. So I don't know if that answers your question.
Thank you. I'm sorry.
Right, oops, there we go. Thank you, just a point and then a question. The point is it was Aberdeen's very own Professor James Clerk Maxwell who proposed a 3-colour photograph, and that was what, 1855 or something. And the very first colour photograph was a few years later to his design, so you should proudly mention that in your talks. My question would be robots, and what robots and artificial intelligence sees of the world is becoming very, very important, because they make decisions for us, or something like that anyway. A robot's eye, is that a cold machine that just sees the facts, or can they be programmed to see what humans see?
Thank you very much for bringing up the point about Maxwell. Actually, when my former supervisor first visited Aberdeen, I actually took her past the plaque that's on Union Street. So yeah, certainly one of the glorious moments of Aberdeen science is that Maxwell was based here before he moved to Edinburgh when he did his most important contributions to color science. Now, in terms of robotic vision, we actually want to design robots so that they help us. So we normally want them to see the world the way we see them if they are to be a helping robot. So for example, a robot that helps a person in the house should have similar sensors to a person so that they can detect properties of objects that are potentially dangerous or useful or interact with them in this particular way. But obviously if you design robots for industrial purposes, then you will equip them with all sorts of science fiction type sensors so that they can clean spillages or do all sorts of things. So there is certainly, I mean, there's a big area of computer vision research where they design these artificial vision systems. And obviously the mega challenge is to make a robotic vision system that is the same as a human. But that's actually very difficult because it's very difficult to teach robots cognitive categories, which we have. So actually the categories of red, green, blue, yellow, banana versus apple versus speech, which also influences how we perceive attributes. So that's the ultimate challenge where we are still stuck. But to teach robots to discriminate, so for example, there is a system that I've recently seen at a conference where a robot can estimate illumination pretty accurately. But then that same robot has done, actually it's all done based on machine learning. And obviously when something is done based on machine learning, which is a system where you, a type of research tool where you actually feed tons of images and the system extracts something automatically from these images that form certain layers of knowledge, and then you actually look to see what the system has learned. It's actually easy to break that system by just throwing different images on it, and that's actually a big challenge. And the weirdest one I've seen is actually a computer vision system that detects a crowd that is rioting as opposed as to a crowd that's happy, and that was used in football games apparently. So that was designed for policing. So it actually can discriminate if people are doing this as opposed to something like this. But it doesn't know what it is, obviously. That the only thing it can tell apart is if there is violence on the terraces. So it's clearly, you know, that there are many still challenges we need to design a robot that can learn, that can be flexible. Because actually, as the previous question was, our vision is extremely flexible and adaptive. And those rules we don't know yet, and once we know them, we will be able to design better systems.
All right, thank you.
I was wondering, you were speaking about the displays that could potentially show things to both colorblind people and normally seeing people, similar things. Is it possible, do you think, to accommodate for different color blindnesses? So not just the green-red, but also, for example, if one person is colorblind in the green-red spectrum, another one is on blue-yellow, for example?
Well, that would be possible by just switching to black and white, which is quite a suboptimal solution. But I think that would be very difficult to solve, because just one accommodation would have to adjust the image to benefit from precisely that part of the distribution which would then be missing in the next person. So luckily, well, not for them because they still exist, but luckily for most of us, in terms of knowing people or having children, it's extremely rare that people have a blue-yellow color vision deficiency, because the short wavelength cones are actually autosomal, so they are not on the X chromosome, they are on just one of the somatic chromosomes, and so it's less than 1%, it's something like 0.3%, it's incredibly rare. It runs in families, so obviously it's inherited in families, and it's very rare. So actually, there's even very few studies of people with S-cone deficiencies because they are so rare.
I just wondered about dyslexia. I've heard that different coloured lenses can help people with dyslexia, and I wondered if that could be incorporated into any screen technology to help people with dyslexia reading.
So I actually had a dissertation student this year who did an experiment precisely on that. We wanted to see, to measure responses from the brain to stimuli that either were presented on a background that was with their preferred color or another color or just black and white. There is a lot of research that goes into that direction. One thing that's interesting is that most people prefer bluish or magenta, pinky type shades for there, so there seems to be a certain level of overlay preferences where they don't really go across the entire range. But actually, when people attempted to do double-blind controlled clinical trial with these overlays, they actually found that it is equivalent to a placebo effect. So that actually people get convinced that this overlay is helping them, and so it doesn't have to be that particular color. So the way they did the study is they got the person diagnosed, but then half of the sample got a different color, and the other half of the sample got the actual color that the doctor said they should get, and the one and then they were told that this was the color, and just through that they all got better. So in a sense, you do get better, but the effect size is equivalent to what is the size of placebo in normal studies. Certainly it's a good thing, but whether it's a mystical phenomenon of selecting a color or whether just any color you like helps you read is something that actually people are trying to work out now.
Any more questions? Okay, I'll give you one up front, yeah.
Since I'm red-green colourblind myself, I'm interested in this area, but when I put those glasses on, it degrades the colour to all intents and purposes. And yet, is it possible to design glasses that upgrades the colour? And if so, would my adaptation then say, it's upgraded, I'm going to grade it back down again, so I don't win?
That's a very interesting question. So, when I was last at the International Color Vision Symposium, they were actually looking at, so the way these glasses work is they actually have a filter that just filters a part of the spectrum at the green level. So it's a fudge actually. So it's another engineering fudge. It's just a simulation, so it doesn't actually give, as the gentleman has rightly noted, it doesn't really give a real experience. It's just a simulated approximation of experience. Also, they work best in daylight illumination. So actually here it's quite dim, so you have this level of feeling degraded, especially as your peripheral vision is where there's a lot of loss of information, so that affects the experience. They are now actually working, I think the military wing of the military research wing, Kinetic, actually they are an outsourced part of the research technology development that used to be a part of the British Army. They are very interested in breaking camouflage. So I have a lot of colleagues actually who work on camouflage, and there the most interesting thing is sort of how do you hide things, and then how do you unhide things. So you want to have a system where your important resources are hidden, but you also want them to be visible to your own people so that they don't destroy them by mistake. So that's actually, I don't know if that answers your question, but there is a development there in trying to simulate various, let's say additional filters or whatever, but ultimately the bottleneck is in the brain. So we can't experience more colors than what is wired in the brain to begin with. So you sort of can enhance vision by using another dimension, such as, for example, you can use lightness to simulate another attribute of the image, or you can use saturation, or you can split a hue into several to enhance edges, or you can use but you can't add more colors to a system that just can see a certain number.